Good evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to the Spot On Weather 2022-23 winter forecast. Part 4 is tonight's video, and I'm going to cover Arctic interactions and take a look at the funny main opener here tonight, this picture from none other than the Christmas Vacation movie, and there's Chevy Chase when he's realizing that, you know what, I probably greased up that toboggan a little bit too much, and he's realizing I'm not going to be able to stop at this point. We can relate it to the atmosphere too, and the fact that tonight's discussion, when I talk about Arctic interaction, is mainly going to be focused on what's known as sudden stratospheric warmings, as well as the stratospheric polar vortex. And, we have a winter where you're looking like Chevy Chase here going down that slope, that hill sledding, where you're just amazed and shocked at some of the weather charts? Or will there be a winter where it's just kind of like, something that we were pretty much getting ready for, we're already ready for anyway? Or are you going to be looking surprised like this? So, real funny start to tonight's video. All right, so let's first talk about these sudden stratospheric warming events. They're abbreviated SSW for short. Now, what exactly triggers this sudden warming within that second layer of the atmosphere? That second layer is known as the stratosphere. It's usually triggered by specific pressure patterns in the troposphere that can send a lot of energy vertically upward into the stratosphere. I'm going to show you an example diagram here in a moment to kind of really go over what type of pressure pattern, synoptic pressure pattern we're talking about that would really disturb that stratospheric polar vortex, really, kick it off and weaken it. Now, in January of 2021, we had a major event, a major sudden stratospheric warming event. This occurred with reversal of winds in the stratosphere. Normally, those stratospheric winds there are from the west, but they actually reverse direction to more easterly direction. And also, there's deceleration of the wind speeds. That's another indicator that we're transitioning from a stronger to a weaker polar vortex. So what happens, look at the middle graphic here in the bottom, showing this sudden stratospheric warming event. Now, these are the 10 millibar temperatures. So we're up in the stratosphere at this point, and note over the polar areas how this maroon and orange coloring. This indicates much above normal 10 millibar temperatures. These are in degrees Celsius. These sudden stratospheric warming events can result in rapid warming of temperatures in the stratosphere. And then just generally when you get that warming over the polar areas, you typically get colder air that is shifted down into the mid-latitudes, parts of Canada, North America, the U.S., parts of Europe. Now, taking a look here, this is the zonal mean temperatures. If you were to look at an actual diagram, by the way, the years are here in the bottom axis here going across. So we look at 1978-79 here. This is your temperature in Kelvin on the y-axis. And so you see a very warm 240 Kelvin reading back in the summer of 1978-79. And then you'll notice these red spikes, right? That red spike, this red line, indicates the 2020-21 sudden stratospheric warming event. These are the 60 to 90 degree north latitude zonal mean temperatures up at that 10 hectopascal level, or 10 millibar level, high up in the atmosphere. Notice this spike which occurred. This is indicative of that sudden warming. This is what it would look like on an actual chart. Looking over here on the right, I'm just giving an example of what a decreasing or decelerated wind speed would look like. This is another indicator that the stratospheric polar vortex is in a weakening state. This is the forecast actually coming up for this particular winter into the early part of the winter into December and January of 2023. This red box outlines some potential forecasts for slower wind speeds in the stratosphere. And so this will have to be something we'll keep an eye on this particular winter. Now, let's take a look at the below diagram here. I talked about in this slide how we look at sudden stratospheric warming, this excessive warming in that stratosphere layer, triggered by specific pressure patterns in the troposphere. All right, these are the particular features that result in that stretched polar vortex, and some of those synoptic features that I was mentioning. First things first, you end up getting this wave amplification over Eurasia. With strength in Scandinavia, you're looking first for that Scandinavian-Ural blocking and a deepening East Asian trough. So that's the first thing I'm looking for here. Notice this high pressure area, this red H on this particular graphic showing the upper level ridge extending northward, high latitude blocking into the polar areas. And that's that Scandinavian-Ural blocking. So that's the first synoptic pressure feature we look for. Downstream of that upper level ridge, we have troughing across East Asia. So once this happens, there's some upward wave energy flux that occurs. So we have some vertically propagating energy that goes from the troposphere up to the stratosphere. And then at point 3 here, we see what that does to the polar vortex. Now that polar vortex is situated there over the polar area, over that North Pole area. And I'm going to get into the polar vortex here in a few slides and delve into that. But I just wanted to show you what happens here. We get the stratospheric polar vortex stretching out, becoming more elongated at point 3. And then some of that reflected downward wave energy flux occurs from the stratosphere back to the troposphere. And then at point 4, we see what occurs on the order of 0 to 30 days after these sudden stratospheric warmings, and we stretch the polar vortex. These are the tropospheric amplifications that we get. So we have at point 4 here, amplified high pressure ridge over Alaska, so another strong high latitude block into Alaska, and a lower pressure trough east of the Rockies, producing cold air outbreaks from the high north latitudes, pretty much cross-polar flow at this point. And that really, that very extremely cold Arctic air goes into the eastern parts of North America. So this is the whole process. By the way, this is courtesy of Dr. Judah Cohen of AR. He's done extensive research on these factors that really do stretch out or weaken the polar vortex. It starts with that sudden stratospheric warming, and then that does a number, or really does work on weakening the stratospheric polar vortex. Now this graphic in the lower right. All right, so now we're going to focus on this. This diagram here, the red colors or those orangish maroon colors, those red colors indicate positive values, and those positive values then indicate higher pressure. Now notice this is January 2021 here on the far left of this graphic. See the upward directed arrow here? That indicates that the higher pressure is building into the stratosphere in early January. Energy is being propagated from the troposphere up to the stratosphere. And then notice what happens by mid to late January, even in early February of 2021, we now see some of that higher pressure or some of that energy flux transferring back from the stratosphere to the troposphere. Look what happens to your Arctic Oscillation Index when we have this wave energy flux coming from the stratosphere, working its way back to the troposphere where we live, where our weather occurs. We have extremely cold temperatures associated with a negative Arctic oscillation. And in this particular year, early January 21, that negative Arctic oscillation extended all the way into mid-February. And I'll show you a temperature anomaly map in this presentation in a little bit, showing what happened with that particular event. Now the blue colors, on the other hand, here, they indicate that they're the negative values. You can see it here on the scale on the right. This indicates lower pressure. So again, the main point here is these positive values, these maroons and orange colors, see the arrows pointing down, descended to the surface by mid and late January. And again, that Arctic oscillation, the AO, is going sharply negative at the same time. Now, let's take a look at what we've got going on this winter. First thing I want to mention with sudden stratospheric warming events, they are a factor in producing a negative North Atlantic oscillation, or negative NAO, and an overall weaker stratospheric polar vortex. Here are the sudden stratospheric warming events per month, extending from November through March. The red vertical bar indicating El Nino winters, the blue vertical bar indicating La Nina winters. And as I went over a couple of videos ago in the winter forecast here on the series, I talked about how we're going into a triple dip La Nina this winter. Notice how during El Nino winters, you tend to have more sudden stratospheric warming events earlier in the winter, like in the December time period. But then as we get into January and February, and even March, notice how the La Nina blue bar here extends higher than this red El Nino bar, vertical bar. So that tells me, January and February are prime time during La Nina winters for these sudden stratospheric warming events. And they range, here's the vertical axis here indicating the number of sudden stratospheric warming events, as many as 5 in January and 5 in February. One thing I want to point out is during La Nina winters, here's my main emphasis, there's more sudden stratospheric warmings during January and February. Now, 10 to 14 days after this type of sudden stratospheric warming occurs, sometimes as long as 30 days, the effects of the sudden stratospheric warming and the weakening polar vortex, those effects work their way back down to the surface and reach the troposphere where we live and where our weather's at. One other important thing to note is not all sudden stratospheric warming events work their way all the way to the surface. We could have a sudden stratospheric warming event and, it's not going to behave necessarily the same way each time. And so we may not get an amplified winter type pattern with all sudden stratospheric warming events. Here is the evolution of a sudden stratospheric warming event. Now this goes back to 2009. So initially 21 to 11 days before the actual SSW, we have pretty much a circular or symmetrical shaped polar vortex in the stratosphere over in the North Polar areas. The blue coloring here is indicating where you have the lowest heights. Those lowest heights are typically associated with the coldest temperature. So this is exactly what you normally would see with a stronger polar vortex. But over time, with those synoptic features that we talked about, the Ural and Scandinavian ridging, those high latitude blocks, that propagated some energy from the troposphere, the wave activity flux from the troposphere into the stratosphere. And look what happens now 10 to 0 days before. Now, see this solid dark arrow here? This is the outline of your stratospheric polar vortex. And notice now how it's being stretched or elongated at this point. Notice how this the orange coloring here indicates anomalously high heights. We're getting much higher than normal heights extending much further north by this point. And then look what's happening here 1 to 11 days after the sudden stratospheric warming event. Look what it did to your stratospheric polar vortex. We now have two lobes, one over in this location to the left, and then one over here to the right, and now the anomalously high upper level heights are situated directly over the polar areas. Okay? What that generally tends to do, these lobes break off. This is called a stratospheric polar vortex split, and you're going to get so much colder air directed to lower latitudes. Here are some more examples of the mean sea level pressure anomalies in millibars of days 0 to 30. And generally what you have is highest surface pressures over the far northern latitudes, over the polar areas, and lower pressures generally in the mid-latitudes, eastern North America, specifically into Europe. This is your surface temperature anomalies. So this is your pressure anomalies, higher heights over the poles, lower heights in mid-latitudes, and troughing in the mid-latitudes. And then the surface anomalies in degrees Celsius from days 0 to 30 after the sudden stratospheric warming event. Colder than normal temperatures in eastern North America, warmer than normal temperatures across the North Polar areas, and then also colder than normal across parts of Europe. So what exactly is this stratospheric polar vortex? It's a band of strong westerly winds that forms in the stratosphere between 10 and 30 miles above the North Pole every winter. It occurs. It's a normal process. The winds generally around that stratospheric polar vortex are going to enclose it. It's a large pool of extremely cold air. Now, when strong and stable, the stratospheric polar vortex generally results in a jet stream staying further north, has fewer kinks in it. Cold air remains well to the north over the Arctic, and the mid-latitudes are relatively milder than usual. But if that stratospheric polar vortex weakens dramatically, that vortex can then be pushed off the pole or actually split into two, which I showed here in this example. The polar front jet stream then becomes weaker. It becomes more meridional or wavy in structure. We get deeper troughs and greater high latitude ridges. And at the surface, you get colder air associated with those cold upper level troughs pushing southward to the middle latitudes. and warm air is going to be drawn up further north into the Arctic. One note here is the Arctic Oscillation, the AO, is often positive with a stronger, stable polar vortex, and it tends to go much more into the negative territory with a weaker, more unstable polar vortex. Now, the vortex overall is going to develop in the fall season each year. In fact, it's developed right now and it becomes the predominant circulation over the North Pole. If you viewed it from above, it would be a counterclockwise circulation, and it generally extends through multiple layers, from the surface all the way up into the stratosphere. The strength of this vortex is going to vary each winter from strong to weak. And in that weakened state, again, that sudden, the stratospheric polar vortex either becomes elongated or it can split into two distinct lobes. In a stronger state, that stratospheric polar vortex remains over that polar area, keeping all Arctic air well to the north, with milder mid-latitude temps for US and Europe. So this is why I'm covering this in the winter outlook. This is a factor we have to look at every single year when looking at the winter forecast. What happens overall with the vortex is as that pressure drops within it, you get increasing wind speed and depth, which occur. Here's an example in the bottom right diagram. The purple shading here, see that more symmetrical shape? This is basically an example of the stratospheric polar vortex. This is exactly what it looks like. Generally, it reaches its strongest point. It continues to strengthen into November and December. The strength is determined by those stratospheric winds at the 10 millibar level. And again, there's your differences between a strong and a weak polar vortex. I won't rehash that again, but you can generally take a look at what this means. Strong polar vortex, mild weather for US and Europe in the mid-latitudes, associated with a positive AO, and a weak polar vortex, weaker jet stream, more wavy, greater meridional characteristics of that polar jet stream, and the coldest air is going to more readily move out of the Arctic into the US and Europe. That's associated with a negative Arctic oscillation, or AO. All right, so in general, let's just talk about how this vortex again weakens. When you get these strong atmospheric waves, vertical propagating waves in the troposphere, they break upward into the stratosphere, and that polar vortex can go from a very strong state to a weakened state. It's weakened so much to be knocked off that North Pole area. And when that happens, the vortex either will slow, sometimes will wobble, slide off that polar area. It can split into multiple lobes, or temporarily even reverse direction, resulting in a spike in the polar stratosphere temperatures. That's that sudden stratospheric warming event I talked about earlier. And following that sudden stratospheric warming, that's when the polar jet stream develops that wavy characteristic or shape with those highly amplified troughs and ridges into the mid-latitudes. And also those ridges extend well up into the Arctic area. These type of highly amplified long waves, troughs and ridges, can then become stationary for days. And by the way, some of these effects of a weakened polar vortex and sudden stratospheric warmings can last on the order up to 2 months. Under the long wave ridges, you typically have warm air flooding north. Those are those blocking ridges I talked about earlier. That warm air floods north into the Arctic while polar air moves southward into those low pressure troughs, those deeper troughs, with the AO slipping into negative territory. Here are some of the strength factors. Now, this is also courtesy of Dr. Judah Cohen of AER. Definitely check him out. The AER website is amazing. He does those blogs on a weekly basis during the winter season. He talks about all these factors, but a lot of his research focused on what really impacts the polar vortex in the stratosphere. And some of the main points he found in the course of his research is summer and early fall Arctic sea ice loss, the fall Eurasian snow cover, if it's increasing, as well as late fall and winter Arctic sea ice loss. So he took a look at all these things. As we know, the Arctic is warming twice as fast as the mid-latitudes, and this is known as Arctic amplification. It's caused by warming global temperatures with climate change. Now, what happens when the polar vortex is weakened? If you meet some of these criteria here, like the Arctic sea ice loss, low Arctic sea ice content or concentration, increased Siberian or Eurasian snow cover, you can get A weakened polar vortex state, you can get changes in the storm tracks across the mid-latitudes, the jet stream configuration, the long wave pattern, the planetary waves overall, and that definitely impacts our weather here at the northern latitudes in the winter season. Now, of course, there are natural variabilities to some of these changes in storm tracks, the position of the jet stream and the planetary waves. We have internal climate modes that occur, and we also have solar cycle changes, which I'll talk more about in my next video. And additionally, we have volcanic eruptions, which can play into the overall planetary circulation pattern. Now, take a look at the upper right-hand graphic here. This shows the 2-meter air temperature anomalies. This is degree Kelvin when we have a strong stratospheric polar vortex. Look at the pinkish coloring here. This indicates well above normal temperatures. This happened to occur in February to March of 2020. The polar vortex was extremely strong, and look at how warm the mid-latitudes are in late winter, February, even into March 2020. Look where the blue coloring is. That's where your coldest temperatures are. They're locked up over the polar areas with that stronger stratospheric polar vortex. Now, bottom right here, look what happens. With a weaker stratospheric polar vortex, we're looking at the air temperatures once again. This was January 5th to the 7th of 2014 compared to the long-term climatological average. The blue coloring indicates much below normal temperatures. The orangish, maroonish colors indicate above normal temperatures. And look at the mid-latitudes now with a weaker stratospheric polar vortex. Blue in the U.S., blue in Canada, blue in Russia, in Siberia, blue in Europe, well below normal temperatures in the mid-latitudes, while places higher in latitudes such as Alaska are well above normal. Places in the Arctic Ocean well above normal. So this is the big difference in the temperature layouts between these two stages of the polar vortex. All right, so now let's take a look here in the bottom left and note how we have something different going on here now. The bottom left, I'm showing a strong stratospheric polar vortex here from February to March 2020. Look how circular, symmetrical in shape it is here. These are your lower heights. These are 10 millibar geopotential height anomalies. And then note the lowest heights are over the poles, period, when you have a stronger polar vortex. Notice that? The purple colors here, highest heights are over the poles. Or rather, the lowest heights are over the poles, and the highest heights are in the mid-latitudes when you have a strong polar vortex. Right, so here's some more examples to show you. On the left, a stable versus an unstable or a wavy polar vortex. Note the changes here. Stable polar vortex, it's strong. It's sitting over the poles. There's no weakening of it, and your polar front jet stream is orientated more west to east. And that floods the entire U.S. continent with mild Pacific air. Whereas a weakened or unstable polar vortex, a wavier pattern develops in the jet stream. Look how deep these troughs are. Look how highly amplified these ridges are. And then you see more troughing that occurs. And so a lot more colder air is going to move south in the case of an unstable or displaced polar vortex as compared to a strong. And then on the right here, take a look at the upper level heights. Look how highly amplified this pattern is for the U.S., where you have an extremely strong upper level ridge situated off the U.S. west coast. And notice the strength of this ridge axis. It goes all the way up into parts of the Yukon territories. And then you have a deep trough downstream from, and look at this blue shading. It goes from the Arctic all the way down to the Gulf Coast pretty much of the United States. Very low heights, extremely low. Coldest temperatures are just going to dive south in this case into the base of this trough. And so this is an example of what's known as cross-polar flow, where you get a direct feed from or connection from the high polar areas into the middle latitudes. This would be an example of a weakened polar vortex situation. Very highly amplitude pattern, wavy jet stream. All right, so now let's take a look at the record strong polar vortex from 2019-2020 winter. Look how circular or symmetrical in shape. We're looking at the North Pole, directly above the North Pole, down on it. This was a record cold stratospheric polar vortex event. Again, this shape, these are the strongest winds here, these white colorings. Looks like a donut, doesn't it? The wave activity flux was unusually low that particular winter, the winter of 2019-20. which allowed that polar vortex to remain relatively undisturbed all winter long. It was accompanied by a positive phase of the AO, the Arctic Oscillation. Look at the temperatures here for the U.S., specifically across the eastern U.S. and New England. Look at this. We had very warm temperatures. Now, this was from January of 2020. I remember just before New Year's Eve that year, at the end of 2019, it was like almost 80 degrees here in the mid-Atlantic because we had this record-strong polar vortex in the stratosphere. Additionally, here's another example from the early January 2021 event showing you how the shape, now this is the geopotential heights. The lowest heights are up over the polar areas, but notice the shape changes. This is December 26, 2020 on the far left. Notice how circular that polar vortex is over the high north, over the polar areas. And then January 5th of 2021, look what happens. Now things are getting stretched. That polar vortex is getting elongated in the stratosphere. And this was the first day of that sudden stratospheric warming event. And then finally, January 15th of 2021, it was complete split. We had one lobe over northern Europe of the polar vortex, and then the other second lobe was over eastern North America. So this definitely highlights, just pay attention to the shape here, and you really get to know what's going on here. This is a fairly strong polar vortex in the stratosphere, and then that sudden stratospheric warming occurs, temperatures spike in the stratosphere. The synoptic pressure systems are in high latitude blocking or in the right places, and you get this elongation, and then you can eventually, if it's strong enough, weakens it enough, the polar vortex can split into multiple lobes. So just wanted to show you what this actually looks like. By the way, these images are courtesy of Laura Siasto of the NOAA Climate Prediction Center. This is a great example. All right, and then here's some more examples. If we look at that particular event, so we looked at how things split, the polar vortex split in mid-January of 2021, and then look at the temperatures. February 15th to the 22nd of 2021, we had extreme cold go all the way down to Texas, Louisiana, Mississippi, all the way down. I'm going to have to fix this real quick. Okay. But we had this occur. Look at the blue coloring here, how cold. Now, this was that crippling freeze situation all the way down to deep southern Texas, the heart of Texas. And I remember this specifically. Houston actually had snow on the ground. Unbelievable with this particular event. And then note the warmest temperatures orange over the North Pole at the same time. See this? Look at that. Look how anomalously warm from Greenland up to the North Pole is. At the same time, all this cold Arctic air is displaced to the south. And I remember how close things were to being very, very interesting across the mid-Atlantic and the East Coast. What happened is the coldest air just basically went straight south from the Arctic into the central U.S. It never quite made it over the Appalachian Mountains because this air is very dense, so it doesn't readily rise over mountainous orographic features. But I tell you what, if this would have been a little bit further to the east, we would have been sitting on a baroclinic zone, and we would have had multiple snowstorms from Georgia up to New England. Yeah, so it was extremely active over here with winter storm events in this particular February of 2021. Here is the minimum wind chills from that. This is actually the late January, February 2019 vortex, that polar vortex that weakened. These are some of the wind chills that went down to the upper Midwest. You might have seen some of the photos in Chicago with that weakened polar vortex, how cold it was. There was literally like steam fog coming off Lake Michigan. Yeah. These are negative 50 to negative 60 degree Fahrenheit below zero. Negative 50 to negative 60 Fahrenheit wind chills. Northern Illinois, Iowa, Wisconsin, Minnesota, and into parts of eastern North Dakota. Just extremely cold when this polar vortex, this particular episode in late January, early February of 2019 occurred. And then this is the couple more examples of weakening polar vortex episodes. Here is the January of 2014 episode. Look how warm it is in the west. All right, well above normal in the western U.S. Well, look at east of the Mississippi River. We're talking temperature departures. These are mean temperatures in Fahrenheit. basically from Missouri to the East Coast, well below normal. The upper Midwest specifically. And then on the right here, I'm showing the February 2021. So I'm showing this same event, February 2021, right here again. These were the temperature anomalies from the PRISM climate database in degrees Fahrenheit. Look at these temperatures. Oh, that's amazing. It did get colder than normal along the East Coast, but what ended up happening is there were any kind of precip that came into the area usually resulted in more of that 40-degree cold rain along the coastal areas of the mid-Atlantic. But yeah, this was some event. All right, and then just a couple more points about the stratospheric polar vortex. Recent research indicates that global warming is leading to a weakened vortex with more frequent outbreaks of very cold air from the Arctic getting displaced into the middle latitudes during the winter season. This is that Arctic amplification I talked about earlier, how the Arctic is warming twice as quickly as the middle latitudes. And when that vortex is elongated off the pole, eastern North America can really bear the brunt of the coldest air during the winter with a direct cross-polar flow or connection to the Arctic. And when that stratospheric polar vortex is split into multiple lobes, the brunt of the coldest air occurs in Europe. So elongation of the stratospheric polar vortex usually favors the coldest air over eastern North America, including the U.S. When that vortex is split into multiple lobes, the brunt of the coldest air usually occurs in Europe. But again, this varies from each event. This is highly dependent on the positioning and strength of the lobes overall. Again, I want to throw my props out there to Dr. Judah Cohen of AER, Atmospheric Environmental Research. It's a great resource. Google that name and you'll be able to see his blogs. All right, that wraps things up tonight on the stratospheric polar vortex. This is a big player in the upcoming winter. It's a big player every year, really. You know, if you have a record-strong polar vortex, chances are it will be very mild across the eastern U.S. this winter. If you have a weakened polar vortex, a weakened one, and look what happens. So, you know, this is going to be interesting. I don't really have any forecast models for the next extended period of time from now into, say, November. But I have been looking at some of the data, and there's already been some favorable synoptic placement of some of these upper-level highs, specifically into parts of the Urals and Scandinavia, which do favor a weakened stratospheric polar vortex. In fact, the vortex is being weakened a little bit right now based on the wave pattern, the long wave pattern, where those upper-level ridges are and how they are interacting with it. So right now, the polar vortex in the stratosphere is really trying to get stronger as we head in deeper into fall and definitely into November, December. But right now, the forecast is calling for a weakening of that stratospheric polar vortex based on those pressure features where the upper-level ridges are occurring into the higher latitudes, the placement of those. We're also paying close attention to the Siberian snow cover as well as the Arctic sea ice. Now, I've decided to do yet one more video after this, and that's going to be part 5. And in that video, I'm going to talk about additional considerations for the upcoming winter forecast. I'm going to talk about stuff like sea surface temperature anomalies. I'm going to take a look at the Arctic sea ice extent. I'm going to look at the Siberian snow cover, and I'm going to look at some other items as well. So I have one more video before I actually get to my forecast for this 2022-23 winter season. So I appreciate the positive feedback I'm getting from everybody. I know I try my best to explain things and break it down into layperson's terms. I felt very passionate about adding one more video to this, a part 5, which is the other considerations for the winter forecast. And then part 6 will be my final assessment, my final verdict for the upcoming winter, where my maps will be in part 6, where I'll show you where I'm expecting the colder than normal temps and the warmer than normal temps, where it's going to be wetter and whether it's going to be dry or not. Right. Lots to talk about. I get very excited. I'm very passionate about these factors. I do a lot of research and studying before I do these videos. Just kind of see what's out there from previous research from some brilliant minds, including Dr. Cohen. But yeah, that's all I got for tonight, everybody. Hope you enjoy the video, and thanks for subscribing to the channel, and most importantly, thank you for allowing me to share this passion with you at home, wherever you're watching the video from. All right, take care, everybody. Until next time, I'll be on to part 5 will be next. I get my numbers right. Take care until the next time. God bless everyone.